In stop 2, we're going to look at motion graphs and how we can represent the motion of an object by a graph. You're going to need the handout that looks like this. It's two-sided. You should see like two graphs on one side and then motion graphs on the other side. We'll actually fold it in half to make like a little booklet. Okay, when we're done, it'll go in our journal, but for now, we can keep it just like this while we write in it. So at the top, it talks about how there are 3 different types of motion graphs: position versus time, distance versus time, and speed versus time. We're only going to focus on 2 in 6th grade, really. You'll get more into the speed versus time graphs in 8th grade. For today, we're going to just look at a position versus time graph and a distance versus time graph. That's what that V in the middle stands for, is a versus, just compared to. Sometimes you might see VS. Okay, so I'm going to just kind of summarize this, but you'll have it here written down if you ever need to come back to it. Okay, so first, a position versus time graph, that shows an object's location compared to a reference point. So an example to think about is if you're driving in a car with your mom and you're driving 30 miles per hour, okay, then if you compare your motion to your mom's, like your body to your mom's body, you would be considered to be not in motion because you're moving the exact same. If you compare your body to a green light or a stop sign or something that's still, that's not moving in the street, then you're going 30 miles per hour. That would be the comparison. If you compare yourself to something else that's moving, just maybe not moving as quickly, say a jogger running down the street, then you could say that you're moving at 25 miles per hour. The point is that you're comparing yourself and where you are compared to a reference point, a specific location. Okay? And we'll do an example of this inside this book. Distance versus time graphs don't compare to a reference point. Instead, they show the total distance covered over time. So if you walk down the hall, you go 30 meters to the water fountain, and then you come back to the classroom, you repeat that 30 meters, your total distance would be 60 meters if you were talking about a distance time graph. You went 30 there and 30 back, so the total distance that you walked was 60 meters. Okay? So if we open this up inside, like this, you see that on one side it talks about position versus time, and on the other side distance versus time. It's the exact same story. Okay, it's describing the motion of you walking down the hallway, and we're going to use this story to create a graph. One will be a position versus time graph, one will be a distance versus time graph, and this will help us kind of compare and see the differences in those 2 graphs. We've got to think back to the beginning of the year when we talked about the parts of a graph and we talked about tails. Okay, remember a title, axis, intervals, label. Okay, we already have a title. Okay, that's kind of given for us. Position versus time. We could also add a more applicable title to the graph. In the story, let's go ahead and read the story first, I guess. So it says, you leave your science classroom to go to the restroom. Your teacher gave you a 3-minute pass. It is 100 meters to the restroom from your science class. The restroom is at the end of the hall. It takes you 30 seconds to get to the restroom. You are in the restroom for 90 seconds. You walk 50 meters in 15 seconds back towards science, then stop to talk to a friend for 30 seconds. You finally hurry the remaining 50 meters back to class in 10 seconds. So if we wanted to create a title for this, we could call it like my walk to the restroom. Remember, the title should be telling someone what the graph is about. Okay. Now, we also have to set up, we're given a blank grid. Okay, so we have to think about each axis. We've got to think about our x-axis and our y-axis. It's always the same when it comes to position versus time graphs. Position is what goes on the y-axis, so I'm going to write position, and time always goes across the x-axis. Remember to leave a little bit of space because we're going to have some intervals on our grid. So in this case, we've got to figure out also our our labels. What are we using to count position and what are we using to count time? So you can see it talks about meters. That's going to be for position. And then it's measuring everything else in seconds. Okay, 30 seconds, 90 seconds, 30 seconds. So for position, I'm going to put an M for meters. For time, I'm going to put an S for seconds. Okay. We've got to figure out our scale, our minimum and our maximum values. So if we think about how far we're going, it says that we're going to the restroom, which is 100 meters away. So we need to make sure that we go starting from 0 to 100. Now if you look, there's 10 lines. So that makes our interval pretty easy. 100 divided by 10 is 10. So we can count by tens. Starting at 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay. Looking at time, it does say that she gave us a 3-minute pass, okay? But we want to talk about seconds, right? So, okay, our teacher gave us a 3-minute pass, but since we're talking about seconds, we want to be sure that we're using seconds down here. 3 minutes would be 180 seconds. If we count each line by 15, if we make our interval 15, that actually works out. So we'd have 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, 180, and that would get us to our 3-minute mark, or 180 seconds. So now we need to read through the story and start plotting on our graph. The first thing it says is that we know the restroom is 100 meters from science class. So our reference point, our 0, is where we're starting, which is our science class. It says that it takes us 30 seconds to get to the restroom. So I'm going to go over 30 seconds, and that's where it took me, how long it took me to get 100 meters. So the first point is going to be at 30 seconds, 100 meters. I want to draw a straight line to connect these 2 points. Okay, you do want to use a ruler or else your line is not going to come out very straight. Okay. The next thing it says that we do is we're in the restroom for 90 seconds. If we are stopped somewhere and we're in the restroom, our position is not changing. This 100 line is representing the restroom. We're just staying there. Okay. If each line is 15 seconds, that means that's 15, 30, 45, 60, 75, 90 seconds. So we're at the 120 mark. Okay, another way to think about that is if we were at 30, we add 90. 30 plus 90 is 120. That line is a straight flat line across the top. Okay, that's showing us that we weren't moving. We were in the restroom for those 90 seconds. Then it says we walk 50 meters in 15 seconds back towards science class. So because this is a position time graph and we're showing where we are compared to science class, we've got to come back down because science class is down here at 0 and the bathroom is up here at 100. So if we want to come down from 100, go backwards 50, 100 minus 50 is 50, and it takes us 15 seconds. We're at 120, that takes us to 135. Again, we want to use a ruler to draw a straight line to connect those 2 points. Okay. The next thing it says that we do is we stop and talk to a friend for 30 seconds. Again, if we're stopped, our position is not changing. 30 seconds would be 15:30 right here at the 165 mark. You can trace that straight line, or you can use a ruler to draw that straight line. Okay. Then it says you finally hurry the remaining 50 meters back to class in 10 seconds. So we're going to go from the 50 back down to 0. We've got to get back to science class in only 10 seconds. This is 15, so you can draw a line close to 180, but not quite there. And then use a ruler to connect the dots. When we look at this position versus time graph, we can see that we started in one location, we moved away, and we came back because we ended at the same starting point. Okay, you only see that in a position versus time graph, right? You can see times where we stopped, times where we were moving forward, and then times where we were moving backward. The distance versus time graph is going to look a little bit different. Even though we're going to use the exact same story, it's not going to look the same because now we're plotting distance versus time. So now, again, same story, so I'm not going to reread it. It's typed exactly the same, but now it's a distance versus time graph. So we can give it the same title, My Walk to the Restroom. Okay, and just like position versus time, how time was always on the x-axis, same thing. So distance is what's going to be on the side, and time is what's going to be on the bottom. Okay, time will always be on the bottom on the x-axis. There we go. So our labels are going to be the same because we're still talking about meters and seconds. So distance in meters, time in seconds. Now our scale might be a little bit different, okay, because we know that we go all the way to the bathroom, which is 100 meters, but then we come all the way back, which is another 100 meters. So we're going to need to be able to go all the way up to 200 meters on our distance axis. So we start at 0 and we need to get to 200. Instead of counting by tens, like we did for our position versus time graph, now we need to count by 20s. So each line is worth 20. 20, 40, 60, 80, 100, 120, 140, 160, 180, up to 200. The time, though, will be the same since we're still talking about that 3 minutes and we're still using the same time frame. So we can do that the same down here. We were counting by 15. 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, 180. Okay. Now if we go up to our story, again it's the exact same story. We're going to go all the way to the restroom in 30 seconds, stay in the restroom for 90 seconds, walk halfway back in 15 seconds, stop and talk to a friend for 30 seconds, and then come back to class in the last 10 seconds. So if we start at 0, 0 is still our starting point, it's still the classroom, right? So it says that we walk 100 meters to the restroom in 30 seconds. So remember, the distance is 100, the time is 30. That's where we put our first dot, and we're going to draw a straight line to connect from the starting point. When we're in the bathroom, when we're still, remember on our position time graph, that was the flat section, a horizontal line. Same thing on a distance time graph because our distance isn't changing, right? If we had like a pedometer or a Fitbit tracker keeping track of how far we walked, when we stay still, the numbers don't keep going. So we went 100, now we stop for 90 seconds. So remember, 30 plus 90 puts us at 120. Okay, so we can trace that straight line or use a ruler. Then, now, when we walk back towards the classroom, okay, that means we've got to keep going up with our distance. That's the biggest change we have from our position versus time graph. Again, think about a Fitbit tracker or your Apple Watch, or if you even just had like an old school pedometer, something that counts your steps and your distance. If you walk back towards the classroom, it doesn't take away the steps you just took, it adds to it. It adds the distance. So we already went 100, now we're walking 50 more meters. So we need to be at 150. It's going to be between the 140 and the 160 mark. And that took us 15 seconds, so we're at 135. So our line should be right here. I'm at 135 seconds, 150 meters. Again, we can connect our dots. And we have our straight line. Then it says that we stop and talk to a friend for 30 seconds. Again, if we're stopped, our distance is not changing. So we have 15 seconds, 30 seconds, okay? And there is a straight line there. Finally, it says we hurry the remaining 50 meters back to class in 10 seconds. So we're at 150, we're going to go all the way up to 200, and it'll be just shy of that last line. Okay, connect our dots. Okay, so we know now that our total distance was 200 meters. If you look at these side by side, again, the biggest difference is that a position time graph, you can have downward slopes, downward lines. So you can go somewhere, you can come back, you can go forward, you can come back, whereas distance will never go backwards. Distance is always going to be going forward, therefore your line is always going to be looking like it's going up. There are some things that are similar, like the stopped or the no motion, these sections, because your position and your distance are staying the same when you do that. So if you fold this back up, this will fit nicely on page 6. It'll be after your balanced and unbalanced forces.